Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're thrilled to have Lovasz here. He was at Microsoft Research in Redmond for a long time, for 7 wonderful years. And well, they were wonderful for us, hopefully for him as well. And he's actually going to talk about some of the work that started at that time. I could take half the lecture telling you all of Lovasz's achievements, but I won't do that. I'll just let him talk about math.
Oh, yes, I think so. Thank you very much. Thank you, Jennifer. And this is really very nice to be back here. And I don't know, it's difficult to talk about these things because there's a lot of background. So today I will be rather somewhat non-mathematical at points, but I will try to at least explain things so that maybe you get an idea of what's going on. Now, this research indeed started here. Here meaning with the people present, which is the more important part of the environment, but it was actually in Redmond, and my main collaborators all had something to do with Microsoft Research in those days. Lovasz was a frequent visitor, and Cauchy-Schwarz Vesztergombi was a consultant, and the others were full-time Microsoft people. So it is clear that large networks abound nowadays in science, and actually that was one of the things that I discovered since I started to talk about the theory of large networks, that how many people in different areas in sociology, history, of course the internet is the basic example, but in many other fields are interested in large networks, and they are trying to they look for help from mathematics. At least provide a language, and then sometimes even provide maybe some mathematical tools for understanding them. So this is I've been invited to quite a few conferences where non-mathematicians who are interested in large networks, from engineers to social scientists. So I will skip this page. It's just kind of why is this really a hot topic? So if you think about, this is still the introductory page, and probably many of you have already seen it, but let's think of the internet, and let's ask ourselves, well, what kind of questions about the internet? We think of the internet as a very large graph at the moment, no other feature, just as a large graph. What kind of features of the internet can we study? What kind of questions can we ask? So with the traditional graph theory, you usually want to know about a graph whether it has an even or an odd number of nodes, because that's an important property. For example, if you of a graph, but of course not of the internet. That's a meaningless question for the internet. Not only because it's uninteresting, not only because it's impossible to answer, but it's meaningless. If I say the internet at this particular second or a fraction of a second, there will be machines which are just booting up. There will be machines which who knows whether they work. So the internet is just not well defined. And of course the same with the human brain or any of these large networks. On the other hand, if we ask how densities, for example, how much is the average degree, that's a perfectly meaningful question. It may not be easy to find the answer, but we can pose the question because it's something which does not change too fast. So what, say, a device, how many other devices are connected to some kind of typical device in the internet? Is it connected? Now that's a trickier question because the answer is almost certainly no. Certainly no. There will be somewhere a router which is down and there are some unhappy people on the wrong side of the router. But that's not what we really want to mean by this question. What we want to mean by this question is whether the internet decomposes into big parts without any connection or with too little connection between them. So for example, when a few years ago there were some cables were severed under the Mediterranean and large parts of Africa were not connected to the rest of the world by the internet, then we could say that for that period the internet was disconnected. Now this is an even trickier question. What are the connected components? Of course, in this case I could say, well, these were Egypt and a few other countries in Africa. But suppose that we are looking at some social network and we would like to discover, or we are about to discover that this network somehow splits into two parts. Maybe there are the, people who are pro-Windows and people who are pro-Linux, and they never put links to each other's web pages. In that case, the internet would be, or that it would be then the web graph would be disconnected, but it would not be easy to answer what are the connected components, because you would have to provide a full list of those people who are in one or the other category, and this is just too large. I mean, you can never create such large lists. So it's not even clear what kind of answer to expect to this question. Is there a meaningful way to pose this question? I would like to show you that there is a meaningful way to pose this question. Now, let's start with the question, how is the network given? So we assume that this graph is huge. And we assume it's not known explicitly. And we don't even know the number of nodes. That's what's called sometimes oblivious testing situation. And why do we assume this? We want to idealize. We would like to define the minimum amount of information under which we can still say something interesting. And so we don't want to know the number of nodes. And now this, I would say that there are two extreme cases, and there's a little but not really too much work in between. So the interesting cases are when the graph is dense, when it has the number of edges is proportional to n squared, where n is always the number of nodes, or the other extreme is when the degrees are bounded. I think that the situation is that the dense case is well developed, is better developed, and I think it's a good exercise case. It's really not what you would like to really learn, because most of the most applications deal with the bounded degree or the low density cases. I mean, most real life networks have this property, but I will talk mostly about, I talk about the dense case, because the methods introduced there are probably quite interesting. There are a lot of interesting results about the bounded degree case, but it's somehow less complete. And I have some hopes that maybe in a decade or so, one would also be able to say something meaningful about the intermediate cases, but right now they are very far from being understood. So it's a dense case. And here is the way the network is given. We assume that we can sample a random node and then another random node, and we can repeat this a bounded number of times. We get a set of nodes, and we can see the edges between the sampled nodes. So in other words, we get a random induced subgraph of some bounded size. And that's all the information we can get about the graph. And the question is, what can we learn about this graph? Now, this was studied extensively in computer science, and there are many people who have contributed to this. And usually the Goldwasser-Ron paper is considered to be the one that introduced this model. But there are both predecessors and successors and so on. And the list is probably it's very incomplete, but some of the key papers. So it's called property testing in computer science, and has been studied a lot. To understand the problem, to appreciate the problem, let's look at the maximum cut problem. So it's an algorithmic problem. You have a graph, and you would like to partition the nodes into two classes, so that the maximum number of edges goes between the two classes, as many as possible. I mean, if you are not a graph theorist, you might find this a little bit unintuitive. You would like to partition usually to have the minimum number of edges going across. And indeed, that's another important problem. But also the maximum cut problem has many important applications. I will not dwell on this issue too long. And this is a hard problem. It's an NP-complete problem. And there's lots of nice applications of it, and some approximation algorithms, and some really most celebrated approximation algorithm is the Gomans-Williamson algorithm, but let's not. I don't have time to go into it, because I want to talk about in the case when the graph is really huge. So, how to specify the cut? So we come back to this question. What is the answer? And so what we would like to do maybe is something like, well, we cannot list all the nodes on one side and then the other. So what we can do maybe is to design a little black box, so that if you go with a question that I have this node of my graph, on which side is it? Is it on the left side or the right side? Then the box will tell you whether it's on the right side or the left side. And of course, it has to be consistent somehow, so that if you eventually ask all nodes of the graph, then it should really give you, well, of course not the strict maximum, but a reasonably large cut, which is close to the maximum. So let's start with a somewhat easier question. Suppose you only want to know how many edges go across, what fraction of all edges go across the cut. So here is this huge graph that is just you don't really see any details of it. And here is a cut, which suppose this cut really has many edges across. Now let's draw our sample. Well, it will have, depending on, I mean, this cut will cut it into two large parts, because of course if it cuts off a small part, then it cannot have too many edges. Maximum cut contains at least half of the edges, and so it must go the middle. And so a good fraction of these sample points will lie on both sides of this maximum cut. And then you look at the edges which go across, before that. So the idea is that, of course, these edges, there will be typically many edges going across. In fact, as it's a simple computation in probability, which will show that across this particular cut, about the same fraction of edges will go from the sample as in the whole graph. And the issue is, could it be that there is a better cut in this, and then you take another sample and there's a better cut in that, and there are all those small cuts in these samples, and why do they have to line up to give a single cut in the big one? So that's the key issue. And in fact, this was a rather difficult result at the beginning of this theory, to show that, in fact, the maximum cut can be estimated by this sampling. I think the best result is that In fact, if you want to estimate it with an error of epsilon, then and that should be an order epsilon to the -4 nodes are enough to sample. So that's probably close to the truth. So you can do the sample, compute the maximum cut in the sample, and then you get an estimate. But now, how to get the cut itself? Before that, I will have to talk about another question. So suppose you have a huge dense graph, and you want to approximate it by something. You want to find a good approximation of it, but some approximation that you can handle. So what could this approximation be? Of course, the natural thing is a smaller graph. Maybe weighted, maybe unweighted. And indeed, this has been done since the 70s, and this leads us to Samaredi partitions and regularity lemmas, which I will just mention. And also, another way is to find representative sets, so some kind of sets of nodes that are somehow well distributed over the whole graph and which are representative of all possible variations of nodes. I mean, a graph has many different types of nodes, nodes with large degrees, small degrees, and so on. And this representative set, you would like to represent all nodes that are there. Now, the other issue is that you want to maybe approximate by larger graphs, provided these larger graphs have simpler structure, even infinite graphs. And this leads to the concept of graph limits, and I will come back to this. So you can sometimes find some infinite objects which are better approximations than any finite object. Now, another preliminary thing here is that here is a graph drawn in a traditional way, and even once it gets above 20 nodes, it's very difficult to see what's going on. So, and you can switch to the adjacency matrix, which is not even, probably even less informative. But then what I do is I replace the zeros of this matrix by white squares and the ones by black squares, and so I get this kind of thing that looks like a crossword puzzle. I call it a pixel picture. And in fact, I view this as the unit square in a coordinate system, which, like matrices, have the origin in the upper left corner. And this is a function with 0, 1 values. So here is a random graph, traditional Erdős-Rényi random graph with 100 nodes and half of the edges, edge density a half. Now this looks pretty similar to a uniform gray, and if we did this on 1,000 nodes, we probably would just see something like that on the right-hand side. But you have to be a bit careful. This is just a chessboard, which also looks like uniform gray, but actually, if you rearrange the nodes and columns, you get this. So this you have to be careful here because there is something arbitrary in arranging the rows, and you would like to find an arrangement which brings out the structure best. So here is the graph which we call uniform attachment graph. It really is a graph where at each step, which grows, at each step a new node is born, and some new edges are born, and the edge density is capped at a half. So that's the frequency of new nodes and edges born. And so you get this kind of picture. And oops, what happened? I'm sorry. Okay, so anyway, that we get that kind of picture. Let's look at that. I'll come back to that picture later. So here is a graph in this pixel representation. And here you don't really see it. It looks like completely random. If you arrange it a little bit, you get a picture like this, where you see that it does have a denser part and a sparse part and then this intermediate part. And so if you cut it into 4 and average out, you get a picture like this. And this is Semiradis regularity lemma explained in a nutshell. Maybe I'll show another explanation of it. So this is the same thing happens here. It's a little bit more complicated graph. So with an appropriate ordering of the nodes, you see this kind of structure. And you cut it into 9 pieces. And what the lemma essentially says is that if you take any of these pieces, inside this piece, it looks like random. Well, there is still some difference between the densities here, but up to an error epsilon, this looks like random. And random means that even if you rearrange, it remains gray. And therefore, so that's what it says, and you have to formulate all sorts of exceptional classes and everything. So it's a rather difficult technical statement, but this will be enough for us. So this is one of these approximation by small by this kind of picture. Here is another approximation by small, and for this, here is this ugly definition. I will try to explain it a little bit. What this definition does, I define a distance between 2 nodes, how similar these 2 nodes are. I pick S and T, and then what I do is I pick another point V, and I count how many common neighbors it has with S, and how many common neighbors it has with T. This is really the expectation of this the adjacency matrix, appropriate element of the adjacency matrix. I take the difference and then the absolute value of the difference, and I take the average over V. So 2 nodes will be close if for most other nodes V, so S and T will be close. For most other nodes V, this V has the same number of common neighbors with S as with T, or almost the same. And of course, it's very strange because somehow, why do you do 2 steps? Why don't you use 3 steps or 1 step and so on? But somehow 2 works as it turns out. So 2 is the right number here. It turns out that this is a metric, and this metric is computable in our model. So if we have this huge big graph and you bring me 2 nodes, I can compute the distance. Of course, with some error, but I can compute the distance just by sampling. That's why I wrote it in terms of these expectations and not in terms of counting or some algebraic formula. And now I define a representative set. U is a set of nodes, so that any 2 nodes in this U have a distance at least epsilon in this distance. And for most nodes, they are closer than epsilon to U. I mean, there may be always some exceptional nodes which you never find, you never see. They behave very strangely, but for most nodes, they are close. That's the dense model, yes.
So this would have remained a metric even if you had been looking at paths of length 3 or 4?
Yeah, that would have remained a metric, of course, yeah. I think, but somehow this is the one which works. And now here is, so for example, how to use this notion to compute a maximum cut. First you construct a representative set U. And that's actually very easy. You just pick points 1 by 1. If the new point is closer to an old point than epsilon, then you throw it out. And if it's farther, then you keep. And the question is how long you have to go. And it only depends on epsilon. It can be bounded by 2 to the 1 over epsilon squared. So it's exponential in epsilon, but it only depends on epsilon. And actually, for most graphs, it's much smaller. It's an interesting question how small it is, and maybe on Friday I can elaborate this a little bit, but not today. So anyway, the point is that this only depends on epsilon. So we are in a league. We are legal. It doesn't depend on the size of the whole graph.
So at the end, you're getting like an epsilon net.
It's an epsilon. Oh, I mean approximate epsilon net. There are some exceptional nodes, but.
Is there something to do with the top singular value or eigenvalue vectors of the graph?
Maybe yes, but yes, but let me go on a little bit, maybe, because at the moment it's not necessarily the size of U. So and now you just work on this U. Oops, sorry. So what is the classes Vi and Vj? For every node of U, I is a node of U, and Vi is the set of nodes which are closer. It's the Voronoi diagram of this U, the corresponding cell. And then you can count how many edges are between Vi and Vj by random sampling. And you count these, of course, approximately these numbers Pij. And then you compute the max cut in this weighted graph. So it's a complete graph with these edge weights. So you can't compute the maximum cut in this. And now each node, if you want to know on which side of its node is, you find its closest representative, and it's on the side where the representative is. So if your representative is a Democrat, you're a Democrat. It's a Republican, you're a Republican. Okay. So this is a simple example of that, but you do have to do some extra work even to answer what even to answer to find the format of the answer of the question. Actually, I should say that there's a different algorithm, but in the same spirit in the basic paper of Friis Cannon. So actually, these representative sets and the regulative partitions are quite close to each other. So here is this your graph, and here is this representative set, and you construct the Voronoi diagram of it, and this is the weak regularity partition. So this is up to some errors a weak regularity partition. Okay, let's go on. Let's come to graph limits. So we want to approximate graphs by some infinite objects, and these are called graph limits. And first I want to explain why these graph limits are needed at all. So let's think of some classical problem in calculus. Minimize this function over the non-negative numbers. And of course, you have already done it in your head, and you see that x equals √2 is the minimum, which is nice, except that it's not rational. So if you have a philosophy that you don't accept any other number than rationals, then what you should say is that this minimum is not attained, but it, of course, can be approximated arbitrarily well. Let's look at another optimization problem. So real numbers are useful. It's a simple optimization problem in graph theory. We have a graph with edge density 1/2, and let's try to minimize the density of 4 cycles in this graph. So if you, in other words, you pick 4 points in a cyclic order, what's the probability that this is a 4 cycle? And you want to minimize this. And now there is a simple argument going back to the 50s by Paul Erdős, which says that this 4 cycle density is always at least 1/16. And it gets close to, arbitrarily close to this, for example, for random graphs, but it never attains 1/16. It's always strictly larger than 1/16. So this is a similar situation, and So this is why these graph limits are useful. So we'll have graph limits for which it is attained. So let me come back to some examples. So what should be these graph limits? So for example, here you have a random graph, again, the same random graph. And as before, we see that it sort of looks like a gray with intensity 1/2. So somehow, if the number of nodes of this random graph goes to infinity, it somehow tends to this picture. Here is another example why you have to be careful. If the number of nodes of the chessboard goes to infinity, it also seems to tend to the gray thing. But actually, if you rearrange it, this will tend to this. And so these are all complete bipartite graphs. And so they tend to this picture. Or if you look at this thing, then this uniform attachment graph, doesn't matter, it's some simple rule that generates them. It turns out that this picture tends to a grayscale image. I mean, these lines are just an artifact of the projector, but it's a continuous picture, and it's 1 minus the max of x and y. Sorry?
It's the least damage they've done.
And so this somehow tends to this function. Now, why is it useful? Another reason why they are useful is that if you know the limit of such a sequence, then you know many properties of the graphs, at least if they are large in asymptotically. As an example, if you want to know the triangle density in such a graph, it will be approximately an integral. W is that function that I pictured there, and you can sort of see what this represents, the triangle, this integral. And so the limit is this integral. So in this previous image, if you want to know the asymptotic number of triangles in this graph, then all you have to do is integrate some simple expression in terms of this function here. So let me now do the math of these limit objects on 2 pages. So we define the density of f in G, and that's the probability that if you take a random map from the vertex set to the vertex set, then this random map preserves edges. So for example, if f is just an edge, then this is the edge density of G, triangle density, and so on.
If G is the complete graph, then every map preserves it?
You have to add loops. If it's a complete graph with loops, then this is 1.
I see.
If a complete graph without loops, then it's a bit smaller. And now we say that this sequence of graphs is convergent if for every fixed f, the density of f in Gn tends to a limit. And okay, there are many equivalent ways of defining convergence, but at the moment I will just use this. But let me mention that this is easily seen to be equivalent to saying that if you take, for a fix a k, and you take a k sample in our model of the graph Gn, you see a distribution on k-point graphs. You see, and if these distributions are convergent for every fixed k, that's equivalent to this. So this is really tells you that this is exactly the right notion in this particular model. Now, the limit objects will form a space which we denote by, a set which we denote by W0, and it consists of all functions defined on the unit square with values between 0 and 1, which are symmetric and measurable. such a function we call a graphon, and for this we get a lot of criticism, but we stand by our decision to call them graphons. And now you can generalize, I mean, you can think of these as generalized graphs, although, or at least weighted graphs, because so the vertices are these uncountably many points, and there is a weight on each edge. If you are willing to go into non-standard analysis, then you can think of actually this as a real graph where between point X and point Y, there's infinitesimal neighborhoods of these point X and point Y. This gives you the edge density between them. And you can even see that it has a kind of extremal form of regularity partition that eventually you get continuumly many classes. This is all just playing around with the view, but this is a simple enough object. We learn about them in college. And so you can define, for example, the density of a fixed graph in W by this integral, where you have seen the special case for a triangle, and it is just generalizes this. So you have a variable for each node, and you can think of it as an expectation of this product. And we say that this sequence of Gn tends to this W if for every f, the density of f in Gn tends to the density of f in W. And so this is so far the definitions. And there are two theorems I want to mention. And the first one is that for every convergent graph sequence, there is a limit in the form of such a function. And conversely, every such function is the limit of a convergent graph sequence. This surprises us a little bit first, because measurable functions are really rather weird general objects, and you would think that maybe piecewise linear or something like that would suffice, but no, you need all measurable functions. And in fact, the limit object is essentially unique up to some technical issue with measure preserving transformations. You can replace x by 1 minus x in the variable, for example. So you have an essentially unique limit object, and you have this notion of convergence. Okay, so in the last part of my talk, I would like to show some newer stuff, applications in extremal graph theory. That seems to be a very active area nowadays. But let me start with quoting a couple of very classical results. So there is Turan's theorem. In fact, this special case was proved earlier. It's a very special case of Turan's theorem. It says that if a graph G contains no triangles, then M, which is, I denote as the number of edges, is bounded by n squared over 4. It's one of the first theorems you learn in graph theory. And the extremal graph has a very special structure. Just split the points into two equal classes, or almost equal off by 1 if the number is odd, and put in all edges between the classes. So that's the largest graph which does not have a triangle. There is a generalization of Turan's theorem due to Goodman, and that also goes back to the 60s. And it says that, in fact, the number of triangles can be bounded from below by an expression which up to some, so this is the edge density, and here is twice the edge density minus 1, and you have to multiply the number of nodes. So anyway, it's some expression in terms of the number of nodes and edges. The key point is that if the number of edges is larger than n squared over 4, then all three factors are positive, and therefore therefore you necessarily have a triangle. There is in a certain sense, an opposite theorem, which is due to cross-current Katona. In fact, it's a very special case, again, of a much, much more general theorem. But it says that if you write the number of edges in the form of k choose 2, you can always do that with some non-integer k, then the number of triangles is bounded by k choose 3. And of course, if k is an integer, then you get exact equality. And the Kruskal-Katona theorem actually tells you exactly what to do if k is not an integer, but I won't go into that. So let's try to see in general what do we know about this relationship between the number of edges and the number of triangles. It's a quite interesting picture. So what I do is that for every graph, I put a red point where the x-coordinate is the edge density and the y-coordinate is the triangle density. So I get lots of points in the plane, and they will fill a shape like this. So what do we know about this shape? So first of all, the upper bound is given by the Kruskal-Katona theorem, and if you work it out, that's exactly the x to the 3/2 function. So this is a nice algebraic function here, x to the 3/2. Now what happens from below? Well, the Mantel-Turan theorem says that, of course, up to 1/2 you may not have any triangles, but from then on it takes off. And the Goodman theorem says that it's above this parabola. And it actually, you get infinitely many points on this parabola, one for every complete graph and actually for every complete bipartite graph with equal color classes. Now the question is what happens in between. So for the Kruskal-Katona theorem, it was also a kind of number theoretic condition on equality, that the number of edges had to be of the form k choose 2. But it turns out that that gave actually points arbitrarily close to this curve. It gives infinitely many points on the curve, and everywhere in between it gets arbitrarily close to this curve. And one would expect that the same happens down here, but that's not the case. It was first Lovasz who proved, very nice result. Maybe I'll come back to it on Friday, talk a bit about it on Friday, is that if you take the chord here between two of these special points, then it's actually above the chord, whereas the parabola is, of course, below the chord. So there is a definite gap between. And then that's from the 70s, and at the same time, Miki Simonovic and I were looking at, and we proved that, we analyzed it in a small neighborhood of 1/2, and we proved that actually it is all even above the chord. And in fact, we conjectured this curve. It's a cubic curve. I won't write up the equation for it. It's some kind of cubic curve that goes here. And we proved that indeed that's the truth for a small neighborhood. And then sometimes around 1990, Fisher proved our conjecture for the first interval, but his method broke down above that. And eventually Razborov, fairly recently, proved the corresponding cubic lower bound between every pair of those consecutive points. And now it's fairly easy to see that this is now the whole picture. So the points are everywhere dense. And another way of saying it is that if I go to graphons, then they actually exactly fill this.
Razborov used a slightly different version of this graph limits.
Yeah. So in fact, Razborov developed this graph limit theory sort of independently and at the same time as either he uses some things differently. Well, I shouldn't say graph limit theory. He developed a graph convergence theory. He didn't construct the limit objects, but that's beside the point. So he used it for this purpose. And recently, a lot of he and some young people who are interested in this subject have obtained a lot of very interesting results using this technique. They solved several long-standing open problems in extremal graph theory based on Rasborov's ideas here. So that was a big breakthrough. Okay, so this is, now these are concrete problems, but my interest now would be to look at some general questions about extremal graphs. In extremal graph theory, this has been studied now for 50 years or 60 years, and you would like to be able to ask some general questions. What kind of general questions? So we had here inequalities between subgraph densities. If you recall the, for example, Goodman's theorem gave an algebraic inequality between subgraph densities, and Kruskal-Katona can be reformulated to give an algebraic inequality between subgraph densities. And so a lot of the dense theory of, the extremal theory for dense graphs involves inequalities between subgraph densities, which usually can be rephrased as linear inequalities. So which inequalities or which linear inequalities between subgraph densities are valid? Another observation is that proofs usually go by Cauchy-Schwarz. That doesn't mean they are trivial. You usually have to come up with very tricky applications of Cauchy-Schwarz, usually several applications. I'll come back to it in a minute. But you can ask, is this really the only technique? Can all valid inequalities be proved using just Cauchy-Schwarz? Is there always an extremal graph? Well, we have already seen an example where there is no extremal graph. So we know that the answer is no, but is there some positive thing that we can say here? And if there's always an extremal graph, or maybe an extremal graphon, which of those are extremal? Which of those occur as extremal graphs? So can you construct an extremal graph problem for which the function x times y defined on the unit square is the solution? Actually not. In this case you cannot. But for other functions you can. So that is a very interesting question. It's an interesting question because if you can sort of characterize which of them are extremal, then for every extremal graph problem, you have an approach where you only have to look for the extrema inside that class.
So these inequalities are always going to be linear, or are they potentially other algebraic functions?
Algebraic inequalities can always be made linear, and I skipped here because this density of, if you take F1 union F2, then the density of F1 union F2 is the density of F1 times the density of F2, the way we defined it. Because just independent events, whether they are mapped. And therefore, it follows that you can always turn it into a linear function. You can replace products by just unions. We'll see an example of that. So let me start with this first question. Still have a few minutes. Again, I need now to make some definitions, okay. So first of all, I need to introduce the notion of a quantum graph, which is just a finite formal linear combination of graphs. So quantum graph is just a sum of graphs with coefficients. And it's another term for which we have been criticized a lot. But here I have a valid apology. It really came from quantum theory. That's Mike Friedman was is working on designing a quantum computer, and for that these graphs actually were states of a quantum system, and this was a mixed state. So it's actually a natural thing. But when we first introduced this, but let me just call this a quantum graph. So quantum graph.
Your most applied work?
Maybe.
These numbers can be negative? Or
They can be negative, just arbitrary real numbers. And if I take any sort of graph parameter, any function defined on isomorphism types of graphs, I extend it linearly over these quantum graphs. And I write x greater than or equal to 0 if the density of x in every graph G is greater than or equal to 0. Now x is a quantum graph, so it's a linear combination, it's greater than or equal to 0. So that's just a general linear inequality, which should hold for every graph G, or equivalent for every graph form. I could put here any graph form. Now, this language allows us to state Goodman's theorem like this linear combination is greater than or equal to 0 all the time, or the Kruskal-Katona theorem to state that two triangles always be three edges. Okay. So here is a question. Given a quantum graph, say with rational coefficients, so that we shouldn't worry about how the coefficients are given, is it non-negative? It's an algorithmic question now. And there's a beautiful result by Hatami and Norin, which says that this is undecidable.
So the support of x is finite?
It's finite. So I give you a finite number of graphs with rational coefficients. Is this linear combination of densities always non-negative? And this is undecidable. It's a beautiful result.
But your definition is for every graph.
Sorry?
I mean, your definition of on the previous slide,
Yes.
or one
Yeah,
previous to that.
Right.
No, no, this one.
You're
Right
thinking of this.
there for every graph.
For every graph. Yeah, of course. Yeah. So if you
there is no number of vertices that is sufficient,
to test, for example,
Yes,
among others,
yes,
this follows.
exactly.
But there's also, you see, of course, if this is not true, that's always provable by exhibiting a counterexample. The issue is, suppose this is true, is this always provable? I'll come back to this in a minute. On the other hand, there is some positive result, which is that it's actually decidable with an arbitrary small error. So if I say that I want to conclude that if either it's non-negative or sometimes it's less than epsilon, well, that's a minus epsilon. And if the minimum is if the minimum of this x overall, I mean the corresponding linear combination densities is between epsilon and 0, then I don't care. And in that sense, it's decidable.
So you should not test more than graphs that have some function of epsilon in the
Yeah.
number.
Yeah.
Yeah. Exactly.
And is that polynomially testable or?
In absolute.
No, I didn't say that. I didn't say that. But, it is not inconceivable that it's polynomial testable, but we haven't worked it out. Now, I want to show you the main trick in Hatami-Norin's proof, because it comes back to this picture. So what is the idea? The idea is that this is the whole situation is analogous with polynomials. Think of this x in the previous slide as a polynomial in n real polynomial in n variables. Well, whether a real polynomial is always non-negative is decidable. That follows, for example, from Tarski's theorem, or it follows actually from the fact that such a polynomial can always be, non-negativity of a polynomial can always be proved by writing it as a sum of squares of rational functions. a finite sum of squares of rational functions, and so it's a proof of this, and there is a proof of course, when it's false, it's easy to prove. And so, on the other hand, if we want to know whether a polynomial is non-negative for every integer substitution, then that's undecidable by the theorem of Matyasevich. So the question is, which is more similar to this? And it turns out that the integer version is, and in fact, the proof goes by reducing this problem, by reducing decision problem with non-negativity of a polynomial to non-negativity of a quantum graph. And the key step is how you get integers into the picture. I mean, this was all very continuous. I mean, these graphones are all. And here is what they do is their variables will be triangle densities in some parts of the graph. And by requesting that you get equality in Goodman's theorem, you're restricting the values to 1/2, 2/3, and so on. And from this, a simple algebraic transformation gives you integers. And then, of course, you have to do some tricky graph theoretic constructions. But somehow it's really lovely that this classical Lovasz's result, which they have to use here, that in between there is a gap that plays a key role here.
So they don't need Borg? It's enough to use the Lovasz result?
It's enough to use the Lovasz result, yeah. It's enough to use the Lovasz result. It's easier to compute with it. Okay, now let's come to the second general question. A few minutes only. Can all valid inequalities be proved using just Cauchy-Schwarz? So, I'll do a little example here. Now, first I will consider graphs that are a little bit more complicated. They will have special nodes, k special nodes, which will be labeled 1 through k, and they can have any number of unlabeled nodes. And I think of this as these are the two nodes through which they communicate with the outside. And then you quantumize them, take formal linear combinations of them, and I look at, this is a linear space then, all k-labeled quantum graphs. I can think of them as some kind of gray thing, which is just a linear combination there. It's an infinite dimensional linear space. Now, I can now introduce a product. If I have two k-labeled graphs, then the product is just a union with the labeled nodes identified. So I glue them together along the labeled nodes. Very simple product operation. And of course, this has to be extended then to quantum graphs by linearity. And I extend this again to any graph parameter. And this is just repeating the definition here. Oh, sorry, it seems, okay. I should have erased the previous slide. It was a repetition. Okay, so here is an exercise. Let's square this expression. Well, it turns out you get back itself back. It's just you do all the computation.
Was there any labeling vertices?
Oh, when a node is dark, it means it's labeled. And I don't write it out, but it sort of should be labeled consistently. Or here is another example, little exercise. This is 3 nodes, one labeled, and then I each put in 2 ways and take the difference and square it, and you get some ugly expression like that. Now take a linear combination, add this to twice this, and you get some ugly, still ugly computation. But now if you, let's ignore the labels here. So make all nodes white. And also let's delete isolated nodes. Isolated node has a density of 1 in everything, so you don't, you can delete it, it doesn't change anything. And what you get is exactly this, what you have in Goodman's theorem, this little combination. And it's a sum of squares, so it's non-negative, isn't it? So it's non-negative, which means that Goodman's theorem holds. Well, of course, for this, you need to know that if a quantum graph X is a sum of squares, after ignoring labels and isolated nodes, then it's non-negative. But that's an easy thing. I mean, that's the easy direction. You just have to use Cauchy-Schwarz, of course. And the question...
are real, right? Because
Sorry?
otherwise your coefficients are real, because otherwise you would...
Yeah, they are real. Yeah,
This is
yeah.
square
This
by
is
ten
real.
x
So,
and complex conjugates.
yeah, it's real quantum. Yeah. And so the question is the converse true? Suppose that something is non-negative, does it follow that it can be written as a sum of squares? I mean, that would mean that everything which is non-negative can be proved to be non-negative using just Cauchy-Schwarz. So this is the question that I posed, and the answer is no, because Hatam in orange result says that it's undecidable, so you cannot have such a proof of non-negativity. But here is the following theorem, which is that if it's non-negative, then it's almost a sum of squares. You can actually write it as a sum of squares plus a little difference where the total sum of coefficients, absolute value is less than epsilon. So, in fact, it says that you can prove it using infinitely many Cauchy-Schwarz. I mean, you tend with epsilon to 0, but that's of course different issue. So this is actually there is an analogous result for polynomials. It's due to Lasserre. It's a fairly recent result. He published it maybe 3-4 years ago, and the proof of this relies on semi-definite programming, and this is why I think that it might be possible to make it efficient, but I don't see at the moment how to do it.
So when you say polynomials, that's not for quantum graphs?
No. I mean, yeah, classical polynomials. So if there's a non-negative polynomial, then it can be written as a sum of squares plus a small remainder term, arbitrary small remainder term. That's also true.
So this is a constructive result, right? So this is, you have an algorithm which has, that's how, it might not be polynomial, what you said, but there is an algorithm which...
the way we wrote it, it's really, there is some going to the limit thing in it, but I hope that this can be made actually constructive. Our current version is not constructive.
But going back to undecidable, why is it not possible that there exists always, for every non-negative x, there exists a collection of y's which makes it inequality in the right direction, but you just don't have an algorithm for exhibiting.
Oh, well, I mean, first of all, you have to argue that these y's would have algebraic coefficients and so on, which is straightforward. And then you just start two Turing machines, and one is looking for a counterexample, and the other one is looking for such y's, and one or the other wins.
So once you know you want the polynomial, you just want to find the coefficients. It's one large linear program or some such thing. So, right?
Yeah, and then
Once
of
you
course
know
you
the
have
degrees,
yeah. If you don't know the degrees, you just try larger and larger, and yeah.
So
this
you
is
say it's not constructive. Is that because you use this theory of this version of Balish to do sort of use non-standard mathematics?
No. It's all within standard mathematics, but in the current version, what we do is we have you can write up an infinite semi-definite program whose solution is exact, but then in order to actually make it into to apply the duality theorem, you have to cut it down to a finite size, and then there is an error there, and we have not made an explicit estimation of the error. I don't think it's impossible. Yes.
Is this
With Szegedy, yes. Yeah. I didn't write out those co-authors who were mentioned on the first slide. Maybe I should have. So anyway, this is so somehow we are able to say something general about extremal graph theory here. And so let's come to the third question. Is there always an extremal graph? The answer is no. We have seen that. Right. But there is always an extremal graphon. And this is actually a nice fact which lies behind this, that the space of graphons is compact in an appropriate distance. So it's a compact metric space. And now the next question is which graphons are extremal. So I should say graphons here. And I'll stop here. That's I won't start with this discussion of this. If maybe on Friday I can say something about this. It's not completely finished, but there are interesting results and questions.
I think we'll definitely take questions, but let me make a quick announcement. So Latsi mentioned several times Friday. On Friday from 1:15 to 4:15, Latsi is going to go into details of this thing. I'd love to see a quick show of hands to see how many people might want to make it, just so that all right, so all right,
No,
sounds good. So we'll probably manage to fit in our, we'll be somewhere on this floor, I think, at the end, but if you don't know where this thing is supposed to happen, send me an email or send somebody you know who knows me an email. Okay, now time for questions.
Is there like a notion of complexity of graphs? Suppose that you have some graph sequence that is obtained by maybe some simple rule like preferential attachment. Does it mean that the corresponding graphon has like some simple function describing it?
It's a very nice question. At the moment I can, okay, so let me go back to a little bit here to where do I want to go back? Yeah, I have to long way. Okay, so here is this distance. You can define this distance on any graphon, because the way I wrote it out, it's actually, you just plug W instead of the adjacency matrix. And this will turn this will define a metric on the 0-1 interval. And I mean, the 0-1 interval in itself is nothing special. I could have defined these things on any probability space. But this actually gives you turns it into a metric space. This metric space may be finite dimensional, may be infinite dimensional. The nice cases are when it's finite dimensional. Among others, then the representative set is polynomially bounded size, and therefore the semi-radic partition is of polynomially bounded size. So you would like to know when it's finite dimensional. We have some results showing that in some cases simple graph theoretic conditions do imply that it's finite dimensional. And we conjecture that for all those, in the last question, which graphons are extremal, I think they are all finite dimensional. That's the sort of one of the main conjectures. So I think the dimension of this space is a possible answer to what you ask. But we don't have a complete result there. I mean, it's just something.
So have there been results on graphs that were proven using graphons?
That?
Have there been new results on graphs that were proven using graphons?
Yeah.
Yes. For example, these results by by Hatami, Gladky, Kral, and Razborov, and Norin. They proved some graph theoretic conjectures. So, for example, one of Aldous's favorite conjectures was that if you have a graph which does not have a triangle, then how many pentagons can it have? Which graph will have the largest number of pentagons? And the conjecture was that you have to take a blown-up pentagon. It's a very natural conjecture, but surprisingly enough, it remained unsolved for 40 years or something. And now they proved it. Now, you can always translate these, of course, back into finite, but the finite proofs have all sorts of error terms and sort of unpleasant details that somehow often disappear when you go to the infinite.
We've also proved stuff about phase transitions in certain classes of graphs that had not been done without. I mean, they're not 40-year-old conjectures, but they're things that, as László was basically saying, are much more obvious when you think in terms of the graph body. It's just, if you tried to go back, it would get to be such a mess you probably would not plow through the proof.
And then there's some large deviation questions on graphs which have been proven by Varadan and collaborators, where the problem was that if you want to do large deviation, it's usually very nice if you have some sequence you want to know something about large deviations, and if your sequence doesn't lie in a common sigma algebra, you don't quite know what random variables to work with. Whereas if you now have these graphons, they sort of give you a unified view of all these finite graphs, so now you have a sigma algebra that describes it, and suddenly you can just use standard large deviation theory to prove things which people didn't know how to prove before.
So is there an analog of the algebraic numbers for graphons? I mean, so if you think of it as the sort of nice subset of the limiting objects.
Well, in some sense, yes. We believe that these, exactly again the answer to the last question, they behave in some sense like algebraic numbers, but the situation is more complicated, so this is more of a feeling.
The feeling is which class of functions?
Those which are extremal for some, so they are somehow, I mean, in one direction they can always be described by or characterized by some simple algebraic equations in this algebra, but the question is the other way around.
Questions? Okay, we'll have 3 more hours of questions on Friday.